So the next presentation is from a leading PVD equipment supplier, Ardenne. We have Sebastian Gatz, Vice President at Ardenne, talking on why PVD technology is the answer to the challenges for IBC, TOPCon, heterojunction, and tandem in gigawatt scale production. Sebastian, the floor is yours.
Yeah, thanks, Shravan. I want to share my screen. And yeah, thanks again for the nice introduction and welcome to my presentation. So first of all, I want to start with a brief introduction of Ardenne. So we are a family-owned company based in Dresden, Germany, provided more than 1,000 coating systems worldwide, having 1,300 employees. And when it comes to photovoltaics, we have an equipment capacity of more than 70 gigawatt in the market, revenue roughly 500 million per year. So more than 50% of the revenue is related to the PV market. But besides photovoltaics, we do also apply our coating competence in other industries such as architectural glass or smart glasses, as well as aircraft industries, batteries, fuses, or electrolyzers. So, but let's focus on the PV applications. Here you do see Ardenne's global footprint as a company and also for the PV market. So headquartered in Germany with our engineering sources. We do have production sites in Germany, China, with strong local support when it comes to service via our entities around the world. So in China, Japan, Vietnam, Malaysia, India, and North America. So far, we provided for the PV industry more than 300 equipment for the mass production of photovoltaics, whereas the capacity is, let's say, divided in crystalline photovoltaics, more than 35 gigawatt, and more than 37 gigawatt for thin film applications. For R&D and pilot production purposes, Ardenne already provided more than 180 equipment globally, so it's not only for photovoltaics. So here you see a very familiar graph for the PV learning curve on the left-hand side, which shows that the model price dropped by a factor of thousands in the last 46 years. On the right-hand side, you see the contribution of equipment manufacturing. So in the year 2000, Ardenne sold PV equipment for commercial application with almost 2 megawatt capacity in average. This year, so 2023, Ardenne sold production equipment with more than 1 gigawatt in average per system. So it's independent on silicon-based photovoltaics or thin film photovoltaics, more than 1 gigawatt. So this is an increase in the productivity of almost 1,000 in the last 23 years. So when it comes to technology, we provide our equipment for different technologies. You see here different phases. For sure, TOPCon and heterojunctions are in the market penetration phase with capacities way above 5 gigawatt per customer. For IBC technologies, we do see also a multiple gigawatt production, especially then next year. However, for tandem, the TRL level is still lower and more in the R&D and pilot stage, even if there are a lot of activities. But we do expect that the gigawatt production for tandem will start from 2025 onwards. So we as a company, an equipment company, we provide our equipment with our technology for the different stages. So you see here and down the HIS system, where it comes to R&D and pilot production up to 100 megawatt, then the Xeonova with up to 700 megawatt capacity, and then the Giganova with up to 1,300 megawatt capacity. So on this slide, you see the basic principle. You see the basic functionality of our equipment, of our inline equipment. Sorry, there's some changes. Where it shows that you have a carrier-based horizontal inline PVD coater. It starts where it goes into the carrier is loaded on the left-hand side with fresh, let's say, wafers. Then it's going into the vacuum where the wafers at the end or the carriers at the end will get in a continuous movement program in the process chamber, where you do the coating on the front side and on the rear side. In this case, it's a front and rear side coating for the heterojunction processes. So the first three, let's say, process unit sections are coating for the rear side, and then you have a gas separation, and then you have 3 sections for the front side coating. At the end, if you finish this, you go out of the vacuum and you can do the unloading of the wafers at the end of the system, or you can use the carrier return system below the equipment and use a lift on the front side and then do the unloading of the coated wafers and then load the carrier again with the wafers and start the procedure from the beginning. So that's basically always the same principle. For sure, we apply different technologies for the different customer needs. For TOPCon, heterojunction, and IBC, we apply rotatable dual magnetron technology, where we apply the tunnel oxide and the doped silicon for TOPCon, either N or P type. For heterojunction, we apply TCO coatings, for example, ITO or AZO. And for the IBC structures based on TOPCon, you use the same as before as a tunnel oxide and the doped silicon, or you can use for heterojunction-based back contact cells a TCO, or at the end also metals for doing seed layer coating for the plating technology. When it comes to tandem, for sure, you can apply the same processes as shown before, but you can add additional layers like the recombination layer, the ETL, the HTA layer, and for sure also the top TCO layer. But besides that, you can use all the evaporation technologies with linear sources, where you can apply the perovskite coatings itself, but also the ETL and HDL by evaporation technologies. And I come to, in the next slides, to some examples of the results. Here in this slide, the TOPCon results, where you do the tunnel oxide coating and the doping, the amorphous silicon, doped silicon PVD coating in one process step. So PVD is a reliable, scalable process. So I showed you before, we can achieve inhomogeneity way less than ±3%. So there are no toxic gases used for, as you may need for other technologies. The big advantage is that you do not suffer from any wraparound for the PVD processes. And you saw a nice presentation last, I think yesterday from Jollywood on this. And for sure, because of this, no edge-back processes are needed. So there are a lot of cost, especially operative and OPEX advantages of these technologies. And for sure, there's no limitation when it, or no really big limitation when it comes to the size. So you see here a productivity equipment with up to 1.2 gigawatt in this case. And you can use this platform to do also not only the rear side standard TOPCon coating, but can use maybe also the front side coating or the IBC coating. I come to this in a minute. But here, as a very straightforward TOPCon process, which is developed from Fraunhofer ISE and IC Constant with a very standard rear TOPCon device, single-side deposition with front busbar design. And we achieved an independently confirmed efficiency of 23.9% and a VOC of 719 millivolt. For sure, if you compare to the records you saw during these days as well, these are not the records, but these are the same efficiency level as the Fraunhofer and ISC have achieved also with other LPCVD or PCVD approaches. However, we see a lot of potential to increase the efficiency, especially when it comes to the fill factor, which is only at 80%. And this work is in progress to do the fine-tuning of the sputter process, but also the emitter profile and the annealing conditions and screen printing design. So if you see this slide, you can imagine that you can use all of the TOPCon coating in the same equipment, not only for the rear side, but also from the front side. So you can apply the coating area, so coating units For the tunnel oxide, in this case, for the rear and for the front side, then you apply a gas separation, and then you finish the rear side polysilicon coating and the front side polysilicon coating, and then you have a double-sided TOPCon device. For sure, you have to apply structuring processes there, but there are smart solutions out there to apply it. And you can imagine also to use this configuration, maybe to just use sputter down processes and to do the coating of the rears of the IBC structure also in one device. So when it comes to heterojunction, you saw all the nice efficiency reports out there. Here we have very standardized production data with busbar design, where our customers achieve VOCs of 750 millivolt and average efficiency of more than 25% and top efficiency of more than 25.3%. For sure, if you get rid of the bus bars and use other technologies, you achieve higher efficiencies there as well. However, OPEX reduction is a critical point here, and this was also mentioned in the presentations before. To get rid of indium or reduce the impact of indium in the overall cost of ownership is a big topic. There are materials out there like AZO, where you can reduce the cost dramatically. However, you also have to look at the long-term stability on the module side, and you see in this case standard AZO-coated heterojunction solar cells in a damp heat test, and you see a power loss after a couple of hours in the damp heat test. However, if you, let's say, apply a layer coating or stack layer coating, ITO, AZO, and ITO, so a triple layer coating, you do not suffer from any damp heat losses, and you end up in the same stability as you do with the standard ITO coating. So with this one, you can apply also directly in these coating devices where you have saving potential of 50% and more, and replacing ITO with AZO. So at the end, I want to also show you the approach where you can start with a copper coating, or let's say it's a layer stack, but it finished with a copper, which you can use as a seed layer for the plating approaches. For sure, you have to think about the structuring and so on and so forth, but there are solutions out there. And this process is developed already a couple of years back with different institutes here, Fraunhofer and CSEM, which is now in production side on gigawatt scale. So this shows by applying sputtering technology, you can reduce or you can get rid of the silver content for sure. And at the end, I want to bring you also some challenges on the tandem devices and why we think that PVD is the right solution for it. For sure, you all know to scale it from single digit centimeter square to wafer or to the module size. This is a big topic for the R&D community right now. You have to achieve the high stability as you are known from state-of-the-art PV. For sure, you have to find a process flow which works in a pilot production to duplicate and do long-term tests on model level. But at the end, the holy grail is to find a cost-effective process flow on a gigawatt scale. And we believe that vacuum process or a combination of vacuum and, let's say, solution-based processes are considered as the right technology approach to meet all these challenges. And you're familiar with this stack. So on gigawatt stage, the mainstream bottom cell is very well implemented. Either is it silicon-based or even also thin film-based technologies, but on top you have to do the additional coatings, either directly on top of the bottom cells or two-terminal, or you coat all these layers stack on glass to apply the four-terminal approach. And we believe that part or most of the layers which you should coat on here on top, so the combination layer, the HTL, the perovskite absorber, the ETL, and a top TCO top contact, or even the metallization, should or can be done with PVD processes. For sure, for high volume manufacturing, there are a lot of requirements to be considered. So low damage, especially on top of the perovskite layer, is one big thing. But you have also to look at high deposition rates and good layer uniformity in the for the layer itself, but also for the interfaces to the layers on top and down there, and especially at lower temperature when it comes to coatings after the perovskite layer. And what you also have to look at that the stability of these coatings should work over a long campaign time. So PVD coaters, for example, working 2, 3, 4 weeks in a row, and then you have to do the maintenance and you have to achieve the same, let's say, results in the first hour as well as after 3 or 4 weeks of this coating equipment. There are a lot of challenges for this, and for sure the damage-free or low damage coating is one thing, and the let's say coating of the perovskite is another thing. And here's an example of this perovskite coating. So you do see here a co-evaporation source, linear source, where 2 different, let's say, materials can be coated with each other. So on the top, you see the basic principle. You have a primary evaporator, which is heated, and then a nozzle pipe, and through the nozzles, the materials is transported to the substrate, either on a coating up or coating down configuration. Both are possible. And the question is now, you can do it in 1, 2, or even up to 4-fold evaporation with our special design. And the question is about the homogeneity of these sources, linear sources. And you see here an example of a source which is scaled to 1.5 meters. So the inhomogeneity over the full area, 1.5 millimeter, is in the range of ±1%. So therefore, it fulfills all the requirements which you need for highly effective solar cell efficiencies. The temperature which are possible is up to 750 degrees centigrade. And for sure, for high productive systems, you also have to look at the dynamic deposition rates. And there we showed these are in the range of 0.4 up to 300 nanometer by minute, and therefore very well suited for mass production. And for sure, for maintenance reason and so on, you have to look also at an easy and fast refill of the crucible. And also this is already solved. So we work on this topic not only on IBC TOPCon, but also on tandem with different institutes all around Europe, and bring this from small, let's say, lab scale up to the mass production. And we are very happy with these results we achieved in the last, let's say, 2-3 years. And with that, I want to bring to my summary, Ardenne serves in the different technology areas, also in the different scaling. So we provide production equipment up to 1.3 gigawatt. For TOPCon, we are on the same efficiency level as LPCVD and see huge cost-saving potentials when it comes to both sides, TOPCon and also IBC structured devices. For heterojunction, efficiencies are above 25% with busbar technology. And for copper plating, either is it on heterojunction or IBC, PVD, let's say seed layer is from our point of view the right solution, and already now in a gigawatt scale. And at the end, for tandem devices, I hope I could show you that there are PVD capabilities available for scaling this technology now to megawatt, and at the end also to gigawatt. So, and with that, I want to thank you for your attention.
Thank you, Sebastian. And this is a very nice overview on PVD technology. So, you know, I've been seeing PVD, your PVD tools since I started working on heterojunction report. You know, the tool capacities have been increasing quite significantly year after year. So is this capacity is technology driven? So that means if you have a tool for heterojunction, so can it support the same capacity for other technologies like TOPCon or you know, for the tandem? The second question is actually, where do you see the limit for this PVD capacity. So right now you are offering over a gigawatt tool. So is it going to be endless? Just two questions.
That's a very good question. So, I mean, for an equipment supplier, it's always important to consider the best overall cost of ownership for our customer, the cell manufacturer, right? And the rule of thumb is that if the productivity of our PVD system is, let's say, doubled, the cost of ownership drops by 30%. So if we sold in 2020 or before PVD systems with capacity of 250 megawatt, and we have now a capacity of 1.2 gigawatts, the cost of ownership decreased by almost 60% in the last 4 years. So from my point of view, we will reach a kind of limit of in the range of 1.5 gigawatt per equipment. It's more a practical limit, such as a typical column spacing in the production halls or increased complexity of the wafer handling. So the applied technologies at magnetron sputtering proved already this outperformance. So you have to look at the inhomogeneities of less than, let's say, 3%. And in some cases, we achieve even 1% over substrate width of 3.3 meters. So in any way, the GigaNova equipment is suitable for customers who produce way above 3 gigawatt. But if you initially produce with a few gigawatt, it is important to ensure that your 24/7 production is well outbalanced. So if you would only have 1 or 2 PVD production systems, these will quickly become your bottlenecks in your production during the maintenance work, and huge buffers will be required. So which in turn would lead to increased costs. So in this case, we would still recommend to stick on the XeaNova platform. So there's a lot of things to be discussed, but to give you a number, I would imagine in the range of 1.5 gigawatt capacity would be the limit.
Okay, great. Thanks a lot. And if there are any questions in the chat window, so please try to answer.
Sure.
Okay. Thank you.
Happy Christmas. See you soon. Bye-bye.